We're going through what I call matrix arithmetic. So we defined what a matrix is. We talked about matrix addition and subtraction and scalar multiplication. We're going to get into multiplying two matrices, not just by a scalar, but a matrix times a matrix. You might already know this or think you know it, but there's actually a lot of subtleties to it. So I'm going to go through a lot of aspects, maybe slowly or too slowly for your taste. But the first baby step is let's just take a matrix times a column vector. A is a matrix, but B is a column vector. And we get a result C. So A is M by N, and B is N by 1. Okay, how do you go about doing that? The standard way is kind of called rows into columns, and here there's only one column. And it's like a dot product. If I say make a vector out of the elements of the first row, I'll dot that vector with the vector made of the elements of B. That's what goes up here. Then I do that for each row. You want to spell it out, here's what it is, but each one of these computations is in effect same computation as a dot product, kind of dotting rows with this one column. Here would be the way to look at it. 2 times 3 is 6, plus 1 times 1, minus 5 times 2, you get a minus 3. You do that for each row against this column. Probably know how to do that already. Here's another way to look at it. Think of the columns of A. Here's the first column, here's the second column, here's the third column. Column vectors. Weighted by the elements of B. The first column is weighted by the first element of B. The second column is weighted by the second element of B. I now have a linear combination of the columns of A. That's another way to look at that multiplication. I'm not saying it's a better way to compute it, but it's another view. And here's a geometric interpretation, which we can do in like 2 or 3 dimensions. Actually, this is a 2-dimensional view. It's not the same vectors as up here. But what's going on geometrically with the linear combination? I have a little vector here going out to the circle. It's minus 1, 1. I have another vector here going out to the green circle. It's 2, 1. If I multiply this guy by 2, I'm up at minus 2, 2. I multiply this guy, the green guy, by 3, I'm up to 6, 3. I add those two vectors, I get this third vector. That's a linear combination of vectors, a geometric interpretation. We're going to be having lots of views of things that you probably think you're familiar with, but there are different views of them. Okay, do this one chart. If you notice, this B had to have the same rows or same number of elements as A had columns. So there had to be compatible sizes. In general, now our B can be any size, well, not any size matrix, but it's not a column vector. A and B are now bigger matrices of compatible size. A must have the same number of columns as B has rows. Kind of an easy way to look at this. If I put the little sizes for each matrix, well, let's say A and B first. A is M by N. B must be N times something else. I'll say P. So these inner numbers have to match. and the outer numbers will be the size of the resulting matrix. So if I multiply this A and this B, the C, or the product, is going to be M by P. If I had a whole sequence of matrices, here I write their little sizes down here. All these inner numbers have to match. N to N, O to O, P to P, etc. Overall result will be this first one times this last one. In this case, M by R. So it's easy to know if you write sizes out, if they are compatible and what the resulting size matrix will be. Matrix multiplication is associative. It's distributive with matrix addition, but it is not commutative. If I knew that A equals B, I could pre-multiply both sides by the same compatible size C. Or I could post-multiply by the same compatible size C. But I can't mix and match. I can't multiply on the left side and on the right side. Got it? So when you do matrix algebra, you've got to multiply in the right order. All right. We'll save the mechanics of matrix multiplication for another video.